Welcome to the Electric Goddess podcast. Thanks for listening in. Today we're going to talk to you about cell selection. Cell selection is one of our most frequently asked questions when talking about batteries, but it doesn't always show up as that question itself. My favorite way that it's been asked is, how many cycles do you get until your cell blows up? That lives rent-free in my head. Mostly the question of how to choose a cell comes up by somebody describing all the ways that they're unhappy with their cell. It's not an easy question to answer, but we want to talk to you about some of the high-level considerations we make when working to answer it.
I'm Luke Workman. I'm Chief Scientist at Electric Goddess.
And I'm Erica Guerrero. I'm the founder and CEO at Electric Goddess. When somebody comes to you and asks you how to choose a cell, what are some common misunderstandings that they might have?
Often people think there's some fundamental chemistry differences between cylindrical and pouch and prismatic, when in fact they're all lithium-ion chemistries. Misnomers like the name Li-Poly for pouch cells adds to the confusion of people thinking that there's a different style of construction, but one's just rolled up and one is die-cut plates or sometimes an oval wound jelly roll as well.
Is there a reason why you would choose one format over another? I know there's plenty of them.
Yeah, if you need high C rates, the pouch format allows uniform voltage drop across each edge of the plate where the tab connection's made, compared to a cylindrical cell where you might have say 6 to 9 feet of foil that's only maybe 7 to 9 microns thick, and you might only have one current tap for each of those foils, so you have a lot of path distance for voltage drop and asymmetry of use of that active material as a result. This is why the same chemistry in a pouch format will virtually always outcycle that chemistry in a cell format. I say virtually always because you could still make mistakes in a pouch format design. But
I want to build a super yacht, mostly, and it has to be electric because, for the brand, yeah. So can you tell me how I would find out my mission profile to even start thinking about a cell selection?
Yeah, you'd have to look at what your intended cruise speed was and what your intended mission distance was, and that would by doing some hull drag calculations for different masses, and you'd have to add to the factor how your increased battery mass affects your drag as well. But you would shoot for optimizing those parameters that you needed based on the vehicle's displacement and hull drag coefficients. And once you knew those values,
you'd know how much power and energy you would need.
That's
basically.
Right. You'd know how much power and energy you need, and that would let you begin selecting what the right cell for the application is. If for some reason you want your yacht to also be able to drag race effectively,
it's a different cell.
Yeah, then it might be a different cell choice. And in cells, you can always trade energy for reduced impedance, or vice versa. You can always give up C rate. You can always give up low impedance to gain energy density. So it's a trade-off that's up to your application for how much is the right amount to give up.
So let's say I handed you pack level requirements, like I need 2,000 kilowatt hours and 4,000 horsepower. Mm-hmm. Is that enough? Like, how do you start translating that to a cell?
Well, we'd look at, your C rate in that application is maybe 2.5 C, depending on if that's shaft output power compensating for motor inefficiencies. If you need that 2.5 C rate continuous, then we would have to validate the performance of different cells that would handle that continuous duty. This would mean that your yacht at that peak horsepower would have only something like 20 minutes or so of runtime at that peak horsepower. So it would be suitable for displays of speed, but if you were trying,
basically,
yeah, if you were trying to get somewhere, there's exponential drag increases with increased speed on holes, and the same battery might actually let that yacht cruise all day at a modest speed and actually cover a lot of ground. So
I've had different scientists, battery scientists, basically show me breakdowns of active materials and different components within a cell and how that helps them choose a cell from the chemistry and, crystal structure, all of it. Is that as important, or like how do you think about choosing a cell? Obviously the specs I gave you for a super yacht people aren't building super yachts yet with battery systems, like full electric battery systems. So even
I bet someone is, but I'd like to think it, please.
Yeah, but even just thinking about like more normal applications, for us might be satellites or aircrafts or even power systems for entire cities. Do you think about it at that chemistry level, or do you take it a bit more higher approach?
Well,
is there merit to each?
There is merit to thinking about chemistry level aspects. However, at the end of the day, all of the cell chemistries can be made to work extremely well. And a lot of that comes down to manufacturing processes and techniques and the design of the cell. Even the additives package to the electrolyte can have a huge impact as well. So, people like to think universally that, say, iron phosphate cycles well. But of course, we've tested iron phosphate cells that were below 80% state of health before 500 cycles. And we've tested lithium cobalt oxide cells that could cycle thousands of times with very little degradation. And so, the consumer, common perception might be that iron phosphate always cycles well and cobalt oxide is always for toy batteries and vape batteries and cell phones that.
But that's not necessarily the case.
That's right. That's not necessarily the case.
There's so many things to consider within a cell.
Ironically, when I'm selecting a cell, one of the things that I care the most about is actually the safety behavior of that cell, with the margins that it takes to provoke that cell to induce thermal runaway, as well as how much energy it releases when it does go into thermal runaway. For the reasons that if the cell has good manners, it enables a higher packaging density for that cell, which can compensate for maybe cell level lower energy density, so that you end up with a higher pack level energy density.
So when you're building out a mission profile, what do you actually mean by worst case scenario? Is it different for each
If
application?
you're making an EV or something, then you have to assume that on the hottest day of the year, some user will hook a trailer at the max weight you're rated to pull with that vehicle and go 70 miles an hour up the longest mountain pass in the country or whatever, So that would be your worst case. What would the vehicle permit to occur to it in a worst case usage model, And that's what you need to thermally design around your battery being able to tolerate.
Is that how far you take it, or do you take it even farther than that to understand your failure margins? What does worst case scenario have to do with trade-offs when selecting a cell?
Well, everybody likes energy. We've never met a client that says, oh, that cell has enough energy and our battery has enough energy. It would be great to just not have more advancement, So since everybody wants more energy density, and one of the ways you can trade to get energy density without any new cell tech is to give up impedance. So this is why very high energy, low C rate cells exist, because if you're powering your laptop, as one example, you might want it to last for 10 hours of discharge, and so your performance at C over 10 in that case is really what matters for that cell. So you can have a fairly high impedance and have just gains in energy and runtime performance. Whereas if you're powering, say, your electric dirt bike, Maybe you want to have 30 horsepower out of a 3 kilowatt hour battery. And in this case, you need something like 10 C cells. So you need 100 times lower impedance to have the same thermal losses. And so in this case, you would choose a cell that's not maxing on energy density. You would choose a cell that has the lowest native impedance. The alternative to choosing a low native impedance is increasing your cooling system's capabilities. However, all of the energy that your cooling system is extracting is ultimately wasted energy that you could have applied for tractive power. This is why there's a balance between C rate and energy. Even in a world where your cells would never overheat, you would still be wasting too much power in voltage sag losses. If you tried to optimize around maxing C rate. Again, the exceptions, of course, would be like in your cell phone or your laptop, where it's supposed to discharge over 12 hours or 10 hours or whatever, in which case you really can give up a lot in impedance. Although if you want the ability to fast charge still, then you would need low enough impedance to not overheat during your fast charging.
So what metrics change for a single cell in a product versus a system, like a battery pack?
Well, in a battery pack assembly, it's so critical that you maintain temperature uniformity between parallel cell groups. Otherwise, they will have asymmetries of lithiation. The warmest places will have the highest intercalation decolation usage asymmetrically, and your cooler cells will not be contributing. So effectively, disuniformity in the pack not only makes for shorter pack lives, but it makes for worse performance of that vehicle serving that mission before the pack fails prematurely. So in a single cell application, you only have intra-cell gradients to deal with, and this makes your life significantly easier. Not that you can't develop significant intra-cell gradients, but as cells get smaller, like in the application of a cell phone or a laptop, the ability to maintain significant gradients across that single cell is low. And so in general, your use of that cell is quite symmetrical. And as a result, you can use that cell to its full potential without leaving the margins necessary if that cell were a component of a larger battery and you had to compensate for the warmest and coolest cells in that assembly of batteries.
Electric Goddess is a business-to-business service provider for battery consulting, design consulting, and test and validation. And we've worked on batteries for companies ranging from startups to Fortune 100 companies. What does the cell selection process look like? Is it fundamentally different from a startup versus a larger company that has more supply chain power? Or is the framework essentially the same?
I mean, larger companies with great developed supply chains have no involvement for us needing to get them the cells usually, which is great, and they can easily purchase from all the major cell makers to get samples. So that's one difference between startups, which often have to hustle and go through lots of meetings and forums and things before a cell maker will ship them samples.
Yeah.
And once you have those samples, fitting the mission is what's most important. So if it's an application where, say, it's like some remote situation where it's never around homes or humans or whatever, then maybe safety is of minimal concern if it's like a deep ocean remote robot or whatever. However, in the situation where the product goes into the general public's operational control of, then you have to validate the safety of that to withstand the most creative kinds of torture that real customers can subject their product to. Not just the classics like stepping on it or dropping it or leaving it out in the rain, but people think of really crazy things to do to their batteries and products.
We talk about quality, safety, and electrical performance as a triangle instead of a ranked list when thinking about cell selection. How can this mental model guide battery teams through cell selection?
Well, essentially, regardless of the cell's chemistry's behavior, whether it's iron phosphate, high nickel, LCO, whatever, if the cell manufacturing quality is risky, if the amount of anode overhang, if the amount of separator overhang, if the winding or stacking tolerance precision is poor, this means this cell is a hazard to use in your product. And if you, for some reason, require using that cell, you would need to do something like CT scanning every single piece to validate that particular cell met acceptable safety.
So as downstream impacts in production rate, essentially.
Yeah, and cost. So essentially, a cell maker who made sloppy cells would need to have something incredibly compelling about their cell to make it worth CT scanning every one of them before you could use that product. With respect to why it's a triangle, of course, the cell's chemistry, when it does thermal runaway, is important. The C rates of the cell, the energy density of the cell, the electrical performance is also important, because if that doesn't serve the mission needs well, then it doesn't matter that it was safe and low cost and whatever. So you have to meet all of those criteria for that cell to be the right one for the job.
So you think about the mission profile as kind of the North Star of that safety, quality, and electrical performance triangle.
I look at the mission profile, particularly with the electrical performance triangle. You've got to find what are my worst case conditions for this mission profile and validate that the cell can meet those needs, including up to what your intended end-of-life condition would be. So you have to age cells and validate that they can meet that mission profile. So this means you have to, if you don't have time to actually age the cells before the product is released, you have to leave ample margin. So you have to run profiles that are actually worse than your real-world worst case to have the representative thermal effects and voltage suppression that you would see on an end-of-life cell's impedance.
So selecting a cell isn't necessarily towards the North Star. It's maybe a constellation that helps with navigation towards where you want to go.
Yeah, and of course, we've so far only considered pure academic and engineering considerations, but cost in many programs is a factor as well. Many of our space programs maybe are somewhat cost
less sensitive.
Yeah, less sensitive. However,
still sensitive though.
Yeah, still sensitive, and many real world programs, whether they're everything from electric motorcycles to aircraft to automobiles, cost is rightly or wrongly a significant driver in cell selection as well.
Well, people have to be able to buy the product, and I know a much younger Luke spent a lot of time doing cost down engineering, which is always a very fun exercise to balance that triangle while also achieving cost targets.
Yeah.
Data sheets are there. That's where most people usually start with cell selection. Can you give me...
I usually trust the dimensions on a data sheet, and every other value
and even
I verify. Yeah, even then the dimensions are usually in the ballpark for dimensions.
Can you give us an example where there's a story of maybe somebody chasing the sexiest number on that data sheet and somehow it hurt their product?
Oh, sure. I mean...
that you can share, of course.
Yeah, people love to chase the highest energy density, and so cell makers have learned their cell gets chosen over other cells if they just fib on their energy numbers a little more than someone else. And so people choose cells over outlandish data sheet values that in their application in practice maybe has lower realized energy going to the load than the cell they were previously using, even which has worse numbers on the data sheet, but perhaps lower impedance or whatever was driving its performance.
So you really need to test your cells before you get too far down the road, so you don't have a uh-oh moment after you have all your parts.
Oh yeah, I mean, I look at the data sheet like a formalized collection of lies the manufacturer writes about the product, and your test results are the only thing that matter. And if your test results at the module level look significantly different than at the cell level, you need to redesign your module, because for some reason, maybe you're overcooling and you have high temperature gradients intracell. Maybe your cooling path involves some cells being fed hotter coolant than others, and you have asymmetries of use. But if you aren't seeing performance that is a representatively scaled version from cell to module, plus the measured interconnect resistance effects, of course, then you need to redesign your current path. Otherwise, there's no fixing that sort of problem in software.
What's the most ridiculous thing you've seen on a data sheet? Outlandish claim.
Oh, I mean, we had a lot of sodium-ion cells that all said at least 6,000 cycles. Some said 8,000 cycles. And then when we cycled them, many of them had puffed and vented before reaching even 50 cycles. And we were running gentler cycles than the data sheet recommended cycling. So that's a pretty egregious lie on the data sheet, I suppose you could say.
And it's not hating on sodium ion as a chemistry, it's just that data sheets sometimes are a little bit optimistic.
Oh yeah. And sometimes data sheet values, if this same effect isn't immune to the electrical component industry. So if you look at
fuses,
if you look at a MOSFET, and it will give you its current, and it will say something like 200 amps or whatever for this MOSFET package, and it will have an asterisk, and you read the asterisk and it says like with dye at 25 degrees Celsius. And so you look into the RTH of the package, and you realize that it had to be on a cold plate that was at like minus 90 Celsius or something for the dye to be at 25 C at equilibrium when it's at that 200 amp rating. And so technically the data sheet's not lying to you. However, those test conditions are probably irrelevant to your usage model unless you happen to be putting it on a cold plate at negative 90 Celsius or whatever.
Going back to the trade-off triangle, is there actually an application where it may make sense to run a less safe cell on purpose?
Yeah, if you have a situation where there's little to no exposure and risk, what I mean by exposure and risk is like if the product goes into people's homes and apartments, then I consider that to be the highest level of exposure and risk, because those aren't areas with professional firefighting, and they may not have, most people's homes don't have sprinklers, and for those reasons, it's like the problem that a single match in the wrong location can torch their whole place. And so those cells' safety really can't be avoided, because the cost of homes doesn't work out in anybody's business plan to keep buying if you're sending a defective product out.
And even just like the public opinion of batteries as well too.
Mm-hmm. So in those situations, cell safety is critical and must guide your cell selection choices. I'd love to say that always as the highest priority above cost, but of course somewhere there's a balance between cost and manufacturing precision and quality. If you have an application where something's like remotely mapping the ocean floor or whatever, those sea gliders or things that do like remote desert mapping or whatever, then maybe cell safety is of minimal concern for your application, simply because the risk and exposure is so minimal that you lose one vehicle or whatever, if it occurs, of course, like...
compared to the benefit of getting those maps
Yeah. Again, though, I bet even the trade-off between losing those vehicles relative to paying another dollar in cell quality or whatever, to make a safer cell, there's probably still an economic decision there, even if you have no risk or liability with what fire the cell may start, or the cell can't start a fire in the application it's used in. I still think you would prefer functionality at the cost of improving cell safety if needed. So when we tear down cells and we see poor manufacturing quality, and we CT scan cells and we see poor manufacturing quality, this is unfortunately something that you basically have to just say no to. It again, we were talking about some applications where maybe you could say yes to it, but I still think the right call is just to say no if you see signs of poor manufacturing quality.
And we're not even talking about like the moral implications of like choosing something like less safe over cost or something.
I was saying just from a business case. Yeah, your company won't survive if if 1 in 10,000 of your products randomly burns a user's home down. You weren't making enough margin on each one of those other 999,000 to buy more homes, and so this is why cell quality needs to be exceptionally high with any cell that you're going to run for virtually any application. Again, I welcome someone to comment some application where it doesn't matter if cell quality. Like I'm sure it exists, but
it's a spectrum, I suppose.
Yeah.
Is there a corner of that safety, quality, and electrical performance triangle that consistently gets underweighed? Like something that people don't think about very often?
I think, unfortunately, there's a lot of selection of cells that doesn't even involve mechanical teardowns to observe quality. They merely check electrical performance and like how consistent they are with the electrical performance of other cells in that lot, And if your cell inspection stops there, that's scary but unfortunate that occurs. Running a safety suite on the cell to validate, say, like what over temperature does it induce thermal runaway, what overcharge quantity before it induces thermal runaway, how many total joules of energy are released in those events and in nail pen, and you need to short circuit the cell, and you need to overcharge the cell. You need to do lots of tests to validate that you have good margins from where your mission operates the cell to where the cell, a do not exceed value. And you don't actually know, no data sheet gives you those. This is the threshold at which the cell explodes values.
It's usually just a pass fail on a data sheet.
Yeah. Often a data sheet, if it mentions any safety test, it'll say like passed this standard or whatever, but that doesn't actually give you any idea of where the safety margins are between your operating parameters on your nominal worst case profile relative to when that cell has a thermal runaway.
I would agree that's a pretty big gap that we see. I mean, it's a big part of our business is understanding what to test and how to test it for the application and the cell that's been chosen.
Mm-hmm.
For sure. I want to double click into quality a little bit. So when you CT scan a batch of cells, what tells you that maybe this cell manufacturer is doing great and you can trust it a bunch versus one that you may have some worries and feel like you might need to be CT scanning before you put it into a product?
I like to see consistent and repeatable anode overhang, and I like to see that the max variation they have in their winding position control is low. Like there's some makers that get as low as say plus or minus 10 microns total variance in winding component, which is incredible, and I love seeing that. Unfortunately, we see cells with as much as say 100 microns or so of winding precision, and if you're a cell with 100 microns of winding precision, you better intentionally leave more designed in anode overhang margin because if you can't control position ultra tightly, then you have to intentionally give up energy density to have a more narrow cathode foil, so that your anode overhang margins are adequate even under your worst case winding conditions, where it's wiggled to one side or the other to the most. So
that's a good example. I think at the highest level, the way that I see it is each cell is very different, and understanding what those variances might be between those cells and what that actually means for your pack design is a whole study in itself.
Yep. And on the topic of CT scans, while a really powerful, helpful tool, and we use them all the time, they don't see the polymers well because they have very little X-ray attenuation. And as a result, doing a physical teardown is still really important, so that you can quantify your separators, uniformity of overhang and overhang margins, and compare that between cells that your maker provides, and you can parameterize quantitatively what their cell manufacturing quality is like.
The last time I checked, NASA uses cells like the MJ1, and that's decades old and could have been phased out by now. Mm-hmm. Why would a choice like that actually be smart?
If you have a mission profile that meets the energy and C rate needs of that old cell, it has some of the best long-term characterization and aging characterization of any cell that's ever been produced, for the reason that it's been used for 2 decades and everything from medical devices to EVs, and
so you're saying that because it's such an old cell, we have so much historical data to essentially show that the cell does what it says it does.
It's not even a particularly safe mannered cell in thermal runaway behavior. It's not a particularly low impedance cell. In fact, there's dozens of cells, maybe hundreds of cells that outperform that cell. But you can look at it like it's a well-known devil you can dance with as your partner. And for some applications where reliability for the mission is ultra critical, they like not having any unknowns left with degradation and aging behavior. So a cell that has literal decades of aging degradation use data is valuable to that application. Because if they were to try to do it without a cell that already had decades of aging degradation data, their mission would be delayed in waiting for a new modern cell to have the same data collected.
Is there anything else you'd like to say about a physical teardown versus a CT scan and what you might get out of a physical teardown other than the polymer?
Physical teardowns, have the ability to measure the separator, and then you can measure attributes of the separator, like its tear resistance and its needle puncture strength and its melting temperature.
And what does that tell you about pack design?
Oh, those all have a big implication on safety. Everybody loves to talk about what is the cathode? Is the cathode LFP or NCM or NCA or LCO or whatever with regards to safety? But in fact, your separators. The choice the cell maker makes for the separator has a really big impact in safety in many different aspects. So that's something nobody even talks about, and the datasheet doesn't even mention that there's a separator in the cell, and yet it's this significant aspect. Of course, electrolyte choices and electrolyte additives package have a huge effect on how the cell will age and cycle long term. Maybe the biggest effect of any single attribute in the cell. And those things are also never mentioned on the datasheet, and people
almost the most critical.
Yeah, like the most critical parameters for safety and longevity are left off, and with respect to the additives package, that's because it's
protected.
It's the secret sauce of their companies.
Mm-hmm.
It's the real reason why some cells perform better than others. and
not easy to
they
reverse
don't share it,
engineer
and
either.
it's broken during formation. It's a sacrificial
Yeah.
additive that decomposes in formation, and so it's a very difficult thing to reverse engineer once it's broken down to form the SEIC.
So we pay attention when we deal with materials companies like separator companies and electrolyte companies. Like they could really have game-changing technologies.
Oh yeah.
It doesn't necessarily help with choosing a cell. It maybe helps more with if you're designing a cell for your application.
Well, it's more like the reasons why some cells do so much better than others when you're running your safety test suite.
Mm-hmm.
And we see as much as a factor of 3 to 1 between, say, they're all 5 amp hour 2170s, and some of them have 3 times the total joules of thermal runaway energy of other cells, even though they all electrically hold the same energy. So, those are reasons why some cells are designed with safer materials and safer electrolytes and safer constructions than others.
So double clicking into safety a little bit, what does the current collector play in the safety triangle?
If you use multi-layer foil current collectors in a stack up, they tend to pass nail pen testing really effectively because they locally are able to vaporize the very thin foil. There's also current collectors where let's say it's a low C-rate application like your laptop or your phone. There's current collectors where they metalize, I think it's a mylar film, and they spray the copper layer on for your anodes current collector, and they spray that aluminum layer on for your cathodes current collector. And when those cells have a fault, when they have a short, like say you nail pen it, you crush it, it has a natural dendritic short, whatever it is. The current collector actually, when it heats, it retracts and it pulls away from the short. And those allow cells to have really awesome safety behavior. They can be very challenging to get to even initiate into thermal runaway without a method like overcharge, for example.
So what does safety behavior give us when choosing a cell?
Well, it gives us what our risk, and you could look at it like quality and safety behavior together are what give you your risk and exposure of choosing that cell for an application. And obviously it has to meet the electrical mission profile as well, but
it makes a difference in packaging, doesn't it?
Yeah. For most of our applications, meeting the electrical conditions are actually the easiest part of the program, and meeting the either the environmental protection needs, the safety requirements, propagation resistant requirements. Those are all harder aspects of the design than simply making a battery pack that can provide the electrical mission load.
Yeah, so even if we had a database of a bunch of different types of cells and understanding their electrical performance, it's not typically, it might point us in the right direction.
Yeah, you'd know which ones were candidates that could meet the mission profile,
Mm-hmm.
And from there it would be a game of which of these have the best manufacturing quality, cost, and safety behavior in propagation tests, and depending on what your application is designed around, you would recreate your real world application conditions and validate the safety performance of those different cells to guide the decision. Then, if all the cells have the ability to electrically serve your needs, then you would make the decision off of metrics like manufacturing quality, safety, and cost.
You said battery safety isn't primarily about cathode chemistry, and I think that's going to surprise a lot of people.
Oh yeah.
Can you break that down a little bit more?
Yeah, people like to universally claim that it's iron phosphate, it can't burn, or it's safe, or we also hear I don't need to do safety testing because I'm using iron phosphate. And you're like, okay, well, if it stores useful amounts of energy, it can release that energy in an unintended path and have a problem. So, we've never failed to induce thermal runaway on an iron phosphate cell.
You actually actively search to fail.
Yeah,
for that. Yeah.
I do. I'm always wanting to find a cell that I can induce into thermal runaway, but so far it hasn't happened. We keep putting.
We've gotten close though.
That's right. There's been some cells have taken extraordinary measures to induce thermal runaway, but then they do go into thermal runaway.
What do you count as going into thermal runaway? Like a white puff of smoke?
No, they have to.
For a cell.
They have to dump their electrochemical potential energy into self-heating.
Okay.
And once they've done that, I consider that completing thermal runaway. There's different stages of thermal runaway though, between cells that just boil some of their electrolyte off to cells that have a thermite oxygen single replacement reaction from their aluminum current collector being used as a fuel, and the metal oxides of their cathode coating being used as the oxygen supply, and those cells will burn tenaciously even under water and cast boiling nickel that they've reduced in that thermite reaction as a byproduct. So, that's a wide range between boiling some vapors all the way to boiling nickel thermite temperatures.
Silicon anode is a hot topic and a really cool material to add to batteries. But we've tested some of them, and some of them have released their entire stored energy in 200 milliseconds.
That's right.
Can you help people understand what that actually means physically and what that delay in time might actually mean?
Yeah.
Or acceleration in time.
When a large cell releases, completes all of its thermal runaway, including that thermite reaction we just discussed, in 200 milliseconds, means that single cell had a thermal power flux of over 40 megawatts. And what that means to the things around it is that even stainless, even tungsten rhenium thermocouples, they were all melted away if they were near the cell in just that split-second moment. So that's about as aggressive as I've ever seen thermal runaway be, leaving behind only bits of the cell's tabs.
Yeah, little bit.
Yeah, the rest of it was like glitter.
So what is
burned glitter?
What does gentle mean when a cell fails? Like, it's obviously a spectrum. Like, if you're able to get almost every single cell, if not every cell, into thermal runaway.
Mm-hmm. Every cell we've ever tested, I've been able to induce thermal runaway. Yeah.
What does a gentle thermal runaway look like?
I mean, a gentle thermal runaway looks like
the separator maybe stopped it, like you talked about earlier.
Yeah, that's right. Like with the example of some pouch cells that I've used for many applications, they have a melting layer in their separator where they have a high temperature material to maintain a strong dielectric barrier mechanically, and they have a layer that melts to close the ionic pores to effectively shut off that cell's ability to drive current into itself. And those cells are able to do miraculous safety tests as a result, like hard short circuit, reverse polarity, repeated nail penetrations, and the cell has little to no, like in a hard short circuit, it gets warm enough that it has to melt that separator, so it reaches like 120 Celsius or so, and then stops getting hot. It's pretty incredible considering many other cells in its category with less safety features built in, enter full thermal runaway under those same conditions.
So do you consider that heating and then stopping heating entering thermal runaway?
This heating has to be self-heating. So they, like if you were doing a heat weight seek or something, which is like one of the worst tests for running safety tests, you would see that inflection where the cell suddenly self-generated heat, and at that moment you would say TR began. And in the case of a nail pen or something, it's a more defined, more defined timing on like the nail went in now. And, we've seen some cells that after the nail went in, they lasted like a minute before they entered TR, and then suddenly they entered TR. And we've seen cells where we nail pinned them 5 times and they never entered TR too. Some cells have
But I thought you said you've gotten
design.
every single cell to enter TR.
I just said nail pin.
Oh, okay.
Yeah.
So it just depends on the method.
Right, like those pouch cells I was mentioning. You can nail pin those things over and over, and they don't enter TR.
I remember seeing them like a beautiful golden cathode as you're trying to disassemble it to discharge it.
Yeah, if you overcharge that cell, it will still blow up just fine.
Yeah.
Or if you hot wire that cell, it'll blow up just fine.
So there's usually a weakness in every cell to fail.
Yeah, so far we've
of the
never failed to
energy.
initiate. Just some have required extraordinary measures.
So that kind of takes me to the accelerated rate calorimetry testing that we do as a baseline in safety. So what is your go-to method for safety characterization when choosing a cell?
Well, if somebody just wants to bound, what's my worst case energy release for this cell? Overcharge is a classic. It usually will pop the highest total joules of energy release value for any cell through any testing mechanism. Another good method is hot wire, because it most realistically simulates the conditions of an actual fault. So people often heat their cell globally, where they try to put the heater to like envelop the cell, whether that's flex heaters wrapped around the cell or whatever. But in fact, a real fault is never some uniform, even heating across the whole surface of the cell. It's usually something glowing red hot in some localized single point on the cell, right? And so whether that's internal cell faults, whether that's wiring fault, shorted balance leads, whatever it is that induced thermal runaway, it usually starts from some single very hot location, with the rest of the cell perhaps not even at a still at room temperature, essentially. So hot wire is another great method for that reason, in that it's a very realistic energy release value, because the conditions are realistic to what an actual defective cell or defective pack build would be like.
And you've embedded fiber lasers into cells to simulate foil edge shorts. Why would you do tests that go above and beyond the standards?
Oh, because it's your due diligence obligation to test what the real fault conditions would be. And having done forensics for 20 years now in failure analysis of batteries, I've seen that it's rarely mid-plane that you have problems. It's usually at the top or bottom of the jelly roll. And in those locations, when you have a problem, once the problem begins, it's able to dump the whole energy of the cell into that pinpoint fault. And so using an embedded fiber optic laser, and the laser is not in the cell, just the tip of the fiber goes into the cell. But by being able to put that light in a pinpoint location there, it's a very representative to real world initiation condition for the most common kinds of cell defects, which would be winding faults at the top or bottom of the jelly roll there.
What happens when people skip, or I should use the word companies. What happens when companies skip early stage abuse testing?
Oh, well, if you get too far committed and you have a lot of cost sunk into using the wrong cell, which we unfortunately see sometimes, there can be a big sunk cost fallacy trap there to try to keep using the wrong cell. But cells with defects, cells with quality issues, cells that don't electrically meet the parameters are all things that you don't fix later in software or whatever. So it's again a situation where the sooner you no matter how far you've gone down the wrong path, the best time to turn around is now.
Definitely. I wanted to touch on a little bit of a thing when it comes to a company going down a path of choosing the wrong cell. And all of our leads are essentially inbound leads here at Electric Goddess. People need our services, and that's why we chat with them. How does that conversation usually go when maybe a company might be a year or two into a program? You can see that it's wrong for their application. How would you handle that conversation?
Well, if I know of an alternative cell, oftentimes I will have already run lots of safety tests on the cell they're using because I've tested many hundreds of cells. And if someone's using a cell that has particularly bad safety manners and poor electrical performance for their application, and I know of a cell that has better safety manners and better electrical performance for their application, then I will try to make just a performance metrics based approach to suggesting a new cell. If I never like to make it about I like this brand better than that brand or whatever, I try to have zero loyalty to any particular OEM, because even the same OEM
can change.
Yeah, the same OEM can actually make some cells that are really high quality and some cells that have a poor track record. So
that was something that was so cool to see, that 5 years ago we did a full teardown on a suite of a cell manufacturer's cells. We send that full report to them, and we were hesitant to use it for many years, and then we opened another one up and they had implemented all of those changes. So continuous improvement is a thing in the battery industry.
I was really glad to see that they had implemented all those changes and that their precision in manufacturing had improved by an order of magnitude from what we saw in their same cells 5 years ago.
I guess it's always, when speaking to a company about this particular issue of needing to change a cell or strategy, it's better to kind of give that harsh truth than the kind lie to advance the battery industry.
Yeah, bad cell selection can end a company, and that's why you really owe it to the client to try to give them the best educated cell selection choice you can provide, even if they don't want to hear that. At that time, nobody likes hearing that what they've already spent hundreds of thousands or millions of dollars, and they've got pallets and pallets of that given cell or whatever. Nobody likes hearing that.
Manufacturing lines.
Yeah, they got manufacturing lines set up where nobody likes hearing that that's a bad choice for that program. However, the sooner they make that change, sometimes that can be the difference between the success or failure of a program. Yeah, that's right. Yeah, be a really big.
Sometimes we accidentally, or maybe not intentionally, offend, but it is a bit of an offensive comment to hear, right, if you're attached to that. But eventually those people do come back, whether it's 6 months later, 1 year later, and you hope that it's not too late.
Yeah.
Just going back to alternative chemistries to cover that, when would a mission profile essentially say you should maybe go with a redox flow battery or a sodium battery, or you hear things like zinc ion, all these news headlines essentially? Why would you choose that over a lithium ion?
Lithium's price keeps coming down. However, it's still more expensive per kilowatt hour than what some battery chemistries are targeting. So if your mission requires, say, the very lowest cost per kilowatt hour to be successful, and the footprint, size, and weight of the system is of minimal importance, then alternative to lithium chemistries can become, that would be their place to shine.
So lithium is still a pretty good battery, though, or an ion.
Yeah, it's an incredible ion for a battery. It's it's as close as you'll get to being hydrogen without the drama of hydrogen. Not that lithium doesn't have its own drama, but it's the electropositivity is extreme, and the size is tiny, so it's kind of the ideal ion on the whole periodic table.
I want to talk a bit about that last portion of the triangle, which is electrical performance. and take a space application. I'd love to go to space one day.
Me too.
Things that we put up in low Earth orbit are 40,000 cycles, basically minimum. And it's one per orbit. So it would be like around with the sun and then the shadow side of the Earth.
Every time it eclipses, about every 90 minutes, you go through a charge-discharge cycle.
How would you approach a cell selection like that for that type of application?
Well, it's an application where you need sealing and you need cyclic endurance. So you would gear your test program around quantifying that the cell doesn't dry up while it's in space, and work to find the right range that you can cycle that cell. And most cells won't do 40,000 cycles of a deep depth of discharge, so you have to find the idealized narrow window depth of discharge that permits that cell to have the cycle life that you need.
And going into voltage window of lithium-ion batteries, like no matter what the mission profile is, whether it's space or the yacht that we were talking about earlier, can you tell me a little bit about how the cell capacities change with that, and how does it work? I've heard you say you trimming off 20% of the cell can give you 3 to 5x the cell's capacity. Like, is that right?
I mean, that's a general rule of thumb that is often true for many cells. There's a field of study that would indicate cycling the cell in the range that has the lowest amount of delta in voltage, so smallest change in voltage relative to the biggest change in capacity. That region in general is the lowest degradation window to cycle that cell in. Now, there's definitely exceptions to that rule, though, which we've found, and this is why you've got to really validate your voltage window rather than just trusting the empirical.
It really seems that there's no way to get around testing in batteries.
Oh yeah, particularly because endurance is largely linked to the stability of the SEI and the CEI, and if the cell has the right additives package to mitigate increased thickening of these layers, and if they have a stable layer, the cell will produce very little gas and it will have very little aging over the life of the cell. So that's something that's largely irrelevant of what the chemistry of the cathode may happen to be, but it's so important in how that cell will tolerate cyclic endurance.
In a world that's changing so quickly too, especially with AI, I've talked to different testing labs that essentially can use predictive models to understand how a cell's capacity might change with voltage window. Do you know some of the mechanisms that might go into a model like that, and would you trust it? Or does it only work because they're using a cell that maybe has a long time of data, like 15 years of use?
That is a very complicated question, and aging mechanics, I've seen such big differences even from 5 degrees C, differences between test groups, and so there's very non-linear effects that I'm not going to say they're impossible to model, but I will at least say they're so input heavy and challenging to model that by the time you've collected the data to model them, you could have also just answered the question you were trying to answer,
and changed the cell chemistry
through empirical cycling. Yeah. Oh, sure.
Yeah, by the time you answer that model, like there may have been an additive change or material change.
That's a real thing that happens. We've watched the prices of cells fall so much. I don't know what the percent per kilowatt hour that it's fallen just in the last couple of years, but I feel like it was significant, 30% or something, maybe more. And in that cost down process, things change, like which electrolyte suppliers are used, which material suppliers are used, and often the data sheet has no changes at all. Sometimes they'll say, like V V.6 or whatever instead of V.5 or whatever, but often there's no indication at all that there was any change to your cell. However, if they change the additives package, your cell may have significantly different aging parameters. And one of the classic challenges that happens in long-term programs that try to do a really thorough job at cell analysis is by the time they've completed this exhausting cell degradation and comprehensive cell degradation analysis, the cell manufacturer will sunset that cell's production to use that line to make their next generation. And this is something that we've seen. It's basically the story of batteries. Is everybody asks for more capacity and faster charging and longer life, and so they don't rest with just making the same cell forever.
So let me summarize a little bit about electrical performance when it comes to modeling. Even if we get the input data set that we need to even understand minute changes that might impact the cell's aging or cycle life, there are more factors that come into play, like environment, meaning temperature, that we don't necessarily even understand ourselves what is happening from a physics or chemistry standpoint, that we would be many years away, what I'm hearing you say, from ever trusting a model over empirical data.
The fundamental reason why trusting a model is hard for me, particularly with degradation data, I'm not questioning their math, but even in an attempt at a physics-based model, as it's not well understood the decomposition products of the sacrificial additives package that is broken during formation to grow the SEI and CEI, as that is not well understood, and that is one of the largest single attributes to the cell's performance and degradation. If you don't know what the surfaces are, then you can't do accurate physics-based modeling. You can make approximations and have compensation factors, and all kinds of things, but and you might be able to make things that predict something really well for a given circumstance, but that doesn't necessarily mean it would predict something well in a different circumstance. Maybe even, again, like I mentioned, 5 degrees C in cycling degradation tests. I've seen it make such drastic differences in capacity retention. So can that model predict where nonlinear step functions are in degradation? It's a tall order.
When is approximation good enough in cell selection?
Well, at some point, you're taking a risk to ship a product with a battery at some point, right? And so even using the very best cell makers in the world, and even if you did individual cell level CT screening, and for every new batch of cells that arrives you run your own safety qualification, you're still not at zero risk. And so for this reason, it's kind of a business decision on where you would end cell qualification. How fast and loose do you want to cut it? What's your risk and exposure level look like?
I'm a fan of lithium titanate cells.
Me too.
Even though they have poor energy density, you can really beat them up.
Mm-hmm.
When would you choose one over an NMC cell in an application?
Well, it's interesting because many of the titanate cells that we've tested are NMC cathode. So they've just changed the graphite of the anode to be that titanate material. And, you choose titanate when you have a situation where bidirectionality of power is important, because they have very high charge rates as well as good discharge rates. And where you need extreme cyclic retention, they also have an advantage in calendar life aging because of low terminal voltage, which is the reason why they have such a penalty in energy density. That same reason is why they have little to no gas production, and they operate below lithium plating potential. And so even if you're charging them at very high rates cold or something, you're still below plating potential. So, there's lots of cool attributes that Titanate has. So an application where safety is important, cycle life is important, and maximum energy density is less of a mission requirement. Also, dollar per kilowatt hour, because Titanates use the same amount of NCM cathode material.
They're expensive.
To make around half the kilowatt hours of storage because of the lower voltage potential.
Right.
They have a cost penalty, maybe even like a $2 to $1 per kilowatt hour penalty over other chemistry. So those are all, applications where it makes sense for the right niche application. Say that you're driving high power in and out of something every 5 minutes for a test apparatus or something.
Like a mining vehicle, trains we've talked about.
Yeah, sure. Applications where you're going to constantly be in use, charging and discharging all day and night, whatever, 24/7. These robots that are running 24/7.
High temperature, low temperature.
Yeah.
They're just rugged.
Yeah, for all of those specialty applications, Titanate could be an excellent choice for you.
So it goes back to mission profile.
That's right. If it's like your electric bicycle and you're trying to make it, on a 20-mile commute or whatever, Titanate might be a poor choice for you because you weren't going to charge and discharge your bike 80,000 times and it doesn't make it all the way to your work commute or whatever, right? So in that case, other chemistries would be a better choice. But if you were, a situation that's like the mining trucks where they only have to discharge them is a really cool Titanate example where they mine from some place that's at a higher elevation where they load the trucks, and then they go down the hill to where they offload the trucks, and the trucks have a net, they regen more energy than it takes them to drive empty back up the hill. And so they don't ever have to charge the trucks, they just have to plug them into discharging stations, which is a pretty cool application for Titanate.
You mentioned lithium plating, and I think it's important to address that for our audience. What does that look like, and how is that important to cell selection?
I mean, visually what it looks like is when you first pull the cell layers apart, it will look like a pretty gold color. But then within a short amount of time, even in an argon glove box, it turns into kind of a tannish color. It will look like tan-colored staining, sometimes growing right into the separator, sometimes distributed on the surfaces of electrodes. Lithium plating is something that, of course, you can force it to occur in most any cell. Maybe Titanate's aside, I'd have to try. But that doesn't mean that it occurs as such a nominal, normal operating conditions occurrence. The cell operating by design. If the cell didn't have side reactions and it was built correctly and it was operated correctly, lithium plating should never occur anywhere through the whole life of the cell. It should be a utter non-occurrence.
So it goes back to quality, electrical profile, and safety.
Yeah.
The triangle.
Like for example, if you didn't have adequate anode overhanging your cathode, then you could build a symmetrical electrostatic field at that edge, which would make a disuniformity in your gradient, so that you could induce lithium plating at a condition that might otherwise be a nominal operating condition that would be safe without lithium plating occurring because of that type of cell manufacturing defect.
Wow. Some people in the industry are pushing back on large format cells. I mean, prismatics are getting bigger and bigger. Mm-hmm. Where do you stand on that?
And for me, it's just about the quality of the cell, whether it's large or small. So whether it's cell phone sized or whether it's some of the monster 40 plus pound cells that we've been testing lately. If their manufacturing quality doesn't look hazardous inside, I'm all right with whatever size the cell is. Where where it brings challenges to pack design can be passing propagation testing with very large high-capacity cells that release tremendous amounts of energy when one cell goes into thermal runaway. It can pose additional challenges. The volume of gas release, the total joules of energy. That can require additional propagation barrier systems to make a design that's safe and resists propagation.
So bigger challenge in pack design,
That's right.
But still the same premises of it's even more important to select your cell well.
Yeah, that's right. With quality of the cell as the cells get bigger becomes even more important because your PPR becomes a bigger challenge to pass with as the cells go up in format. Doesn't mean impossible, and doesn't mean you can't still end up with great pack gravimetrics. Just means you have to account for greater energy release volumes that'll happen at the same moment. Whereas if it was a bunch of little cells, the odds that many of them would all go simultaneously is low. So normally you would have some sequential series of them going, which would mean you never had a sudden very large hot gas release and or fireball release.
We've talked about PPR, or passive propagation resistance, especially in our intro to battery pack design episode. Can you just tell me at a high level what is PPR and why is that important to cell selection?
PPR, or passive propagation resistance, means that you intentionally induce a cell in a portion of the battery into a thermal runaway condition, and you validate that this doesn't spread like a chain of firecrackers in a one cell triggers the next until all the cells have entered thermal runaway. This is kind of your worst case safety test outcome for a battery design, and so
naturally it's harder with a larger cell to contain one cell full of energy.
Right.
That used to be many cells.
Yep, not impossible, and again the ratios of the material and weight needed don't have to be bad either, but yeah, it is often more of a challenge to design.
And why is cell selection important to pass this PPR test?
For the reason that for cells of the same chemistry and the same size format and the same watt hours, we see in the range of say 3 to 1 on what their energy release looks like. And the time constants of that energy release can be an even bigger variant, maybe even a whole order of magnitude. So for these reasons, some cells are much more, I mean, crudely, you could say like poor manners in the safety test. Like if their sides split open and shoot plasma into their adjacent cells, that's
rude.
That's rude. That makes a condition that you have to add extra spacing with extra, we like to use potting materials with an endothermic and intumescent resin between the cells. However, that means we need to use, if the cell has a tendency to side rupture, just as one example, that would mean we needed to have wider cell spacing and use additional potting between those cells to still pass PPR. So if a cell has, excellent safety manners, like some that we've tested that only vented out their intended vent path, which is quite remarkable because most cells' vent paths are like a rough suggestion if the cells should fail out of that area or not. So
I think it's remarkable that over the 20 years you've been designing and building and validating batteries, you've never built the same battery twice.
That's right.
And each one is super different. So when it comes to calendar aging versus cycle aging in a cell, which one catches you off guard most? Is it like, how do cells die?
Calendar aging can be really tough to anticipate on programs that have a short lead time.
Yeah.
Often you're trusting the cell maker's data, at least preliminarily, for the reason that they're the only ones that had prototypes of that cell to begin.
Long enough.
Yeah, calendar aging or early, and when they make tweaks to the cell, then those calendar aging validation data, is no longer valid, and even tweaks to, 25 ppm of different additives to the electrolyte can make a huge impact in the stability of that cell. How it ages, what side reactions, how much gas is produced, and so for those reasons, it's calendar's really tough to do on a short timeline.
Is impedance rise related, and is that something that causes or catches people off guard too when it comes to an early death of a cell?
Yeah, many applications. I don't know if more than capacity, maybe the same amount as capacity. Not that I've done a statistical analysis, but of packs are end of life because of impedance climb.
And what does that look like when it comes to the cells?
From a user perspective, it means that you try to use the product, and after a short while, the battery's either overheated or has shut down from voltage sag issues.
So even if it has calendar or cyclic ability, the impedance rise can stop operation.
Yeah, and remember, calendar life is not merely capacity loss; it's impedance climb too. Mm-hmm. So calendar degradation affects both attributes. We were mentioning SEI growth. That's one of the phenomena that causes calendar decay mechanisms, and as that SEI layer continues to grow, your impedance climbs and your capacity is reduced at the same time. So,
what's one electrical test that you run that maybe other industry people might skip and they shouldn't?
Well, I used to run fairly low current impedance measurements, but now I try to run mission representative currents for impedance measurements. And, many would squawk at that, saying, the cell will be in a transient for temperature during those pulses, and because of this, the data will, not be accurate. But in fact, when you measure the data that way at those mission profile specific impedance measurements, it actually correlates best with the application, because under the real application's load, it will also have those same rising temp transients. So that's something that most of industry would want the cell to not have any thermal transients during that measurement, and I understand why, and I did that for many years too. It's just that value is less representative of matching the real applications with respect to using that impedance for thermal calculations in particular.
Impedance is a hot and complicated subject for sure. And I know that there's an impedance value on data sheets typically as well that's pretty low.
Usually it's a 1 kilohertz AC value, which is somewhat unrelated to the DC current handling of the cell.
At what point did you stop trusting those impedance values and recognize that you needed to?
The first time you see a one, say that at 1 kilohertz it says the cell is 10 milliohms or something, and the moment that you apply a load to it for a few seconds and you measure your voltage drop, and you see that maybe it's 3 times, maybe it's 4 times more voltage drop than that 1 kilohertz number would predict, and right away you realize, wow, this number is a useful number for doing a quick spot check to see if this cell has the right electrode area and it's all been wetted, but it does not really have a bearing on the electrochemical performance of the cell.
Would you say that the battery industry is getting smarter about cell selection than it was, say, 5 years ago?
I hope so. There's more tools than ever. CT scans, the cost barrier's really fallen, so that doing quality inspections now, there's really no cost reason not to do it. And
we see cell manufacturers making updates as well.
Yeah, that's right.
Improving on the quality and safety.
Yeah, no cell maker can survive for long making defective product, And so for that reason, continuous improvement is critical as a cell maker.
And it's also very difficult to manufacture cells in general.
Oh yeah, you have delicate coatings applied to very thin foils. Some current collector foils are as thin as 3 microns these days, and working with foils that are like 6-7 microns is already very tough. They're so thin. So lots of challenges. Even air motion disturbs the foil and causes potential electrode cracking and things.
Our clients at Electric Goddess are brilliant people that figure out amazing things and eventually can figure out cell selection for themselves too if they're not already. And what is the difference between what we do here at Electric Goddess or what a testing lab or an internal team might do when choosing a cell?
Well, most companies, and again, this is a generalization. I know some do have their own calorimeters, but most companies don't have their own in-house ability to quantify cell safety between one to another with quantitative metrics. Maybe they induce thermal runaway and observe it or video it or add a temp sensor or something, and that's worth, that has value and it's worth doing. But if they want to know real data on, say, gas evolution rates, what species of gas are generating thermal runaway, total joules of energy, then it takes a pretty specialized piece of equipment and pretty specialized techniques. So that's where a lab like us fits that situation real well.
I would say we really excel at determining what the mission profile is and what needs to be tested. And then once we have all the data, because we have the tools to gather the data here, or we can make it ourselves pretty quickly with the experience that we have, you're able to analyze all of that and give them a real look at what decisions they're making in cell selection. Because everything's different.
It changes it from being, we use these ones because we like this brand or we like this sales guy, to these are the quantitative metrics of the safety behavior, the cyclic behavior, the mission profile, temperature behavior, and you can make a decision based off of metrics entirely that way.
I think a thing that we see as well is that somebody might say, at my last company I used this cell and we've been shipping for a long time, and then as you kind of dig underneath that, you get to see they don't actually know how those decisions were made and if the product is actually doing well today. And so definitely good to validate your cell selection.
Even validate from your lots too, because we've seen sample cells sample cells that you get from Korea and they're great, and then when you get production quantity from their Chinese factory and it is in fact a different cell using different materials and has different performance than what you validated from a different factory's line.
And related to cell selection, as my closing question, with over 20 years in batteries, Luke, I think you have a great reputation within the industry. What is something that you know now in regards to cell selection that you wish you would have known even 10 years ago, 20 years ago?
There's so many tricks, everything from cell teardown tricks that I've learned to how to resin encapsulate them and section them to do microscopy anywhere in the cell. One single thing I would tell myself, I guess, is make an arc calorimeter sooner. I've only had an arc now for 10 years, and if I would have had an arc 10 years before that, I would be ahead of where I'm at now on cell safety.
Oh, we can thank our friends Felix and Dominic and Kevin for giving us the opportunity to build it.
That's right.
Thank you so much, Luke. It's been a pleasure running this business with you for over 7 years together. Thank you.
It's an honor. I would pay admission to get to come to work every day. I love it.
I love it. Should we shake hands?